So this is for number 4. And in number 4, the question that's asked... number 4, about this tank of water. The question that is asked is about the resultant force on the 10-meter angled face at the right bottom of the tank caused by the pressure of the water. So we know that the pressure of the water is acting on, these surfaces, and if we were actually to plot, let's say pressure as a function of depth, that there would be a linear line. Oops. Well, don't put an arrow there. But these pressure vectors would, look like this on the surface, and we know that pressure equals the density times the gravity times the distance into, if we're measuring z in this direction, the distance into the fluid. The same is true down here. We've got some pressure acting on this surface, and at a point it's the same as the pressure perpendicular to the surface, like this, and this pressure increases as we go down in depth. So the question is, what is the pressure acting on this surface? And it tells you in the problem that this thing right here is a 10-meter pool. Basically, it goes 10 meters into the plane, or into the piece of paper. So we know, pretty much we have to memorize this, that the pressure, this is our shortcut, the pressure on a submerged surface is equal to the pressure evaluated at the centroid. Okay, that's what it's equal to. But it's not, of course, this is not the same as where it's acting. So this is really the pressure, the value of pressure on the submerged surface is the value of the pressure acting at the centroid. Since this is essentially a square, it's a square that is 10 meters by 10 meters. We know that the centroid of that square is literally in the center of the square. So we need to evaluate the pressure at, this is 8 meters, so this must be 12 meters. The pressure at 12 meters plus an additional 5 meters would be equal to the pressure on the submerged surface, equals rho times g times 17 meters. Okay, so that's equal to 1,000 kilograms per meter cubed times 9.8 meters per second squared times 17 meters. I've not been doing so great at the math in my head, so I'm just going to take a look at that. That is on the order of, I'm going to call that 10,000 times 20, 200,000. Okay, if I had to guess, 200,000. But, it's going to be more like 170,000. I'm guessing, I'm compulsed to guess, I see. Okay, so that we've got meters squared in the top, kilogram meters per second squared, and this becomes meters squared. So kilogram meters per second squared we know is a Newton, and that is over meters squared. Newtons per meter squared, that's what we want for pressure. Let's go ahead and, what is that? I wanted to change the color here. So we have 1,000, and I'm going to multiply that by 9.8, and multiply that by 17. Oh, looky, we have 167,000 roughly newtons per meter squared. I said 170,000. Oh, that's not too terrible for me. So the pressure is 170,000 newtons per meter squared. We know this is about 1.5 atmospheres. Is that about right? We know that for every 10 meters of depth, that's about 1 atmosphere. We're a little over 10 meters. We're at 17 meters, so a little over 1.5 atmospheres. Perfect. We're in the right ballpark.